Hi, everybody. This video, 3.6, related rates, is one of my favorite topics in calculus. But just like in the previous video, I mentioned that we couldn't teach implicit differentiation until we did chain rule, and I couldn't teach, and similarly, I could not have taught related rates, which I'm about to teach, without chain rule. No, without implicit differentiation. Well, both. Anyway, we're going to be using implicit differentiation to do these problems. These are problems where you're looking at. Well, let's just jump in. You'll see. I'll explain as we go. So here we have let's look at the first problem. A 26-foot ladder is placed against a wall. You see it right here. If the top of the ladder is sliding down the wall at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? Now, you may think that if the top is going down at 2 feet per second, that means the bottom is moving out at 2 feet per second, but it's not that's not necessarily the way it works. You could have as we're going to see, you could have the bottom going faster or slower than the top, and it could vary at what angle the ladder's at. As you'll see. Anyway, so let's solve this with let's just solve this now with a little math. So we have the equation x squared plus y squared equals 26 squared. Now, where did this equation come from? Well, there's this little guy named Pythagoras, and they named the theorem after him because you have the ladder, which is on a diagonal. If you go straight down the wall, and then straight out from the wall to the, bottom of the ladder, base of the ladder, that forms a right triangle. And in a right triangle, a squared plus b squared equals c squared. So x squared plus y squared equals 26 squared. Now, once we have this equation, that's really what you want to do. You want to find an equation. In all of these related rate problems, we always want to find an equation that sort of ties together all the different variables. So now I'm going to differentiate everything. Now, am I going to do y in terms of, am I going to differentiate y with respect to x with respect to y? The answer is neither. We're going to differentiate both of them with respect to time, because that's what we're talking about. We're talking about a related rate. So the derivative of x squared with respect to time is going to be 2x times dx dt. That's the chain rule, and the derivative of 2y with respect to time is 2y dy dt, and the derivative of 26 squared is just 0. It's a constant. So this may seem, wow, what have I done? I just made this big giant mess, but really it's not such a big giant mess, because we know x and we know y. They're giving us that. They're saying it's 10 feet away from the wall. And now, if it's 10 feet away from the wall, that means x equals 10. And I can figure out y at that point with Pythagorean theorem, because if the ladder is always 26, that never changes. So 10 squared plus y squared equals 26 squared. I could easily find y. And we know how fast it's going down, so I know dy dt, because we know it's going down. So since y is shrinking, it's not 2 but -2 feet per second. And let's go right here. And we have, so let's just do it step by step. So 10 squared plus y squared equals 26 squared. That's the Pythagorean theorem. We're going to use that to find the value of y when x equals 10. And that's going to give us by crunch, 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 and we're going to get exactly 24, which is very nice. No radicals or no rational numbers, blah blah blah. So so back here, I know my x, I know my y, I know my dy dt. All I got to do is solve for dx dt, and we're done. So really, at this point, it's actually very, very simple algebra. So let's just go to it, and here we go. So dy dt, as I said, is -2, x equals 10, y equals 24. I'm going to plug that all into this equation, and I get, drum roll please, dx dt is equal to 4.8 feet per second. And again, it's exactly 4.8. That's not an approximation. It's not a radical. It's exactly over there. So Related rate problems, basically, as you do a lot of them, and I am such a kind person. I want you to understand the math so well. So I give you a lot of homework. I've given you a lot of homework in this, so you can have practice doing all these problems and become an expert at it. And you'll notice that there's always a bunch of variables, and you have to find that you have to come up with a formula that ties all those variables together. In this case, the formula that tied everything together was Pythagorean theorem. Then you differentiate everything with respect to time, and usually they will give you all the information you need. They'll give you all the numbers you need, except for one thing, and that's usually the one thing that we have to solve for, which is what the problem is asking for. So that's kind of a common theme. So what we did in this problem is really going to be kind of a common theme, for all of these related rate problems. And I hope you can relate to this. I get it, relate. Alrighty, so let's we're over here. Okay. Suppose that now we're doing example 2. Suppose that 2 motorboats leave from the same point at the same time. One travels north at 15 miles an hour. The other travels east at 20 miles per hour. So they're not headed away from each other, they're headed at a right angle. Going up one's going, but you get my point. Sorry for me. Anyway, so that's what's happening here. And how fast will the distance between them be changing after 2 hours? So if I look at the picture, basically they're forming this kind of they're really kind of forming this right triangle sort of, and the distance, if I would have a string connecting the 2 boats, how fast is that string increasing? That's really what the question is. So let's so this looks very Pythagorean theorem-ish to me, because you kind of have a right triangle, because here's one boat going east, the other boat going north, whatever it was, and this is the diagonal between them. So we know that this distance, we're calling it z. We call this distance z, which means ultimately we're going to want to find dz dt, the rate that z is growing. But step at a time. Z squared equals x squared plus y squared. I get that from the Pythagorean theorem. And now I'm going to differentiate this the same. So I have my formula, which ties together all the different variables. I know that dx dt equals 20 because they gave us that. I know that dy dt is 15 because they gave us that as well. And we want to find dz dt at the end of 2 hours. So I need to find out how big is x and how big is y. What does x equal and what does y equal at exactly 2 hours? And then I'll do Pythagorean theorem. I'll see exactly how big z is, because we're going to need that. Look, but why am I going to need that? Because when I differentiate both sides here, we're going to get 2z dz dt plus 2x dx dt plus 2y dy dt. Now, they never gave us x, they never gave us y, they never gave us z at that point, but I could figure it out easily, because if it's 20 miles an hour and I'm traveling for 2 hours, then x is going to have to be 40. And if this is 15 miles an hour and I'm traveling for 2 hours, then y is going to be 30. And if x is 20 and y is 30, I do a little Pythagorean theorem here, and I'll get z is 25. So I'm sorry, z. What is z? What is z? Let's see, 20, 3, 4, 5, 3, 4. No, 25. Right, z is 25. So. I'm looking at the wrong things here. Sorry about that. 40 and 30. I'm sorry. Z is going to be 50. I take it. X is going to be 40. Y is going to be 30, and Z will be 50. It's kind of like a 3, 4, 5 triangle times 10, if you think about it. Anyway, now we have everything we need except for Z. But at Z, I get, if X is 40, Y is 30. We just plug in Pythagorean theorem because Z is 50. Now I plug everything into this equation. 2 times 50 times dz dt. Dz dt is what we want to solve for ultimately. Equals 2 times 40 times 20 plus 2 times 30 times 15. Crunch, 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 and you get dz dt is 25 miles an hour. So that is pretty good. So the boats are going to be separating at a rate of 25 miles per hour, meaning that the rope that's between that's connected between these, there's no rope actually, it's an invisible rope. But that invisible rope, that theoretical rope, is increasing at a rate of 25 miles per hour at that point. I'm not saying the whole time. Now, surprisingly, it's not going to be 25 miles per hour the entire trip, but specifically at the point. See, these rates change. The rate of the rope is going to change as the position of the boats change, and that's the way it is. That's why you need calculus altogether. Otherwise, it would just be an algebra problem. Alrighty, let's look at example 3. So we have a point is moving along a graph. That's interesting. A point is moving on the graph. So we have a graph. So instead of having a real problem with boats and ladders and stuff like that, a real physical problem. So we have, well, this could be a physical thing. If I have a circular track, whatever, and a point is moving along the graph, x squared plus y equals 25. So I have a graph of a circle, and there's a point moving on that graph. When the point is at -3, which is right over here, the point that's over there is x coordinate is increasing at a rate of 0.4 units per second. How fast is the y coordinate changing at that moment? So we're going to view x as a function of time, and we're going to view y as a function of time. X squared plus y squared equals 25. Differentiate everything with respect to t. I get x squared plus y squared equals 25, 2x dx dt plus 2y dy dt equals 0. Divide everything by 2, and now for x, I'm going to plug in -3. That's what they're giving us. Y is equal to +4. They gave us that as well. The x dt is 0.4. Now I just got to solve for dy dt and crunch, 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 and I get dy dt is 0.3 units per second. Easy peasy, lemon squeezy. Okay. Now let's relate this to business. Because a lot of, as you know, a lot of this class is focused to business applications, and probably a good number of you are business majors or want to be business majors. Not necessarily all of you, but some of you may be. But probably a good chunk of you are. Anyway, related rates in business. Suppose that for a company manufacturing flash drives, the cost, revenue, and profit equations are given by C equals 5,000 plus 2x, R equals 10x minus 0.001 x squared. And we know that P equals R minus C. That's a general thing. Profit is revenue minus cost, and which is a general truism, I guess. I always thought that was just a definition of profit. But anyway, but notice that since the cost and the revenue are constantly changing as x changes, so the profit constantly changes at each point. Anyway, so where the production output in 1 week is x flash drives. So they make x flash drives every week. So x is how many flash drives they make per week. If production is increasing at a rate of 500 flash drives per week, now increasing, that means that the derivative is 500. Not that the value is 500, but the derivative is 500 of x. So the x dt would be 500. Anyway, when production is 2,000 flash drives, so the 2,000 production is 2,000. That means the x value would be 2,000, and the x dt would be 500. So find the rate of increase in cost, the rate of the increase in cost, revenue, and profit at that point. So if production x is a function of time, and it has to be because it's changing with respect to time, obviously it's a function of time, then C, R, and P must also be functions of time because they're functions of x, and x is a function of time, so you do the math. You do the math, get it? I thought that was my job. But my job is to teach you how to do the math. So these functions are given implicitly rather than explicitly, so here we go. So cost is equal to 5,000 plus 2x. So if I take the derivative here with respect to time, I get dc dt is equal to 5,000 is equal to the derivative of 5,000, which is just 0, plus the derivative of 2x, which is just 2. So dc dt is equal to 2 times dx dt, because that's like the inner derivative thing again. And solving that, I get the x dt is equal to, since we know that the x dt is equal to 500, when x equals 2000, which I explained, we get it from that line. Then dc dt is going to be 2 times 500, which is $1,000 per week. So cost is increasing at a rate of $1,000 per week. Imagine your cost is increasing at a rate of $1,000 per week. Now revenue, and then let's see what revenue is doing. Hopefully, I hope that revenue is increasing more than that. So revenue is 10x minus 0.001x squared. Differentiate both sides. The RDT is equal to DDT of 10x, which is just 10, and then times dxdt, minus DDT of 0.x squared, which is 0.002x times dxdt, and factor out the dxdt, which is what I'm going to want here. 10 minus 0.02 times 2x equals the RDT. Now, dxdt is equal to 500 when x is equal to 2000. Again, that was given to us, so I could plug those numbers in. So dRDT is going to be 10 minus 0.002 times 2000, because that's what x is, times 500, because that's what dxdt is. I'm getting from this guy right there. And if you crunch that all out, you get 3,000 a week, which is good, because you know, the revenue is increasing more than the cost. And now the rest is like super simple. Now it's just a question of subtracting. Profit is revenue minus cost, so it's just 3,000 minus 1,000. So the last question is actually the easiest question. It's just straight subtraction. 3,000 minus 1,000 is 2,000, and the profit is increasing at a rate of $2,000 per week. So in this situation we described, your profit is increasing. So even though your cost is increasing, but your profit is increasing, or you're making a profit, and you're increasing your profit. So that's a good thing. All righty. Although, what do I know about business? I assume business, you want to make a profit. Well, that is the end of related rates. I hope you related. I hope you can relate to it. Those are funniest. I'm so funny. It cracked me up. For some reason, I never understood. Other people don't appreciate my jokes as much as I do. I crack myself up, what can I say? Anyway, that's it. 3.6. Have fun. We'll see you guys next time. Yay.